No. We're going to continue on with this is chapter 11. Chapter 11 deals with bond theories. There's pretty much done with 10, except we're not completely done with 10 because we need all of 10's material for chapter 11. But we're done with 10 because we finished the bond energies and bond lengths, and that was the last part of 10. There's one other thing which we'll talk about, estimating delta H, which I didn't talk about in chapter 10, but we'll do that later. Chapter 11 deals with bond theories. What is a theory or theories underlying bonding? Really, we should just label this bond theory. Because the theory that describes bonds and molecules is quantum mechanics. And the part about theories comes from two ways that quantum mechanics is applied to bonds. The first way is molecular orbital theory. Molecular orbital theory, this is the full quantum mechanical treatment of bonding and molecules. So this leads to, things about the structure of a molecule, the what we call energies. Energies, we have different energies that we look at, but one of the energies that we consider is the energy of promoting electrons that are electron-electron transitions between orbitals. And so this is spectral data. When I say spectral data, spectroscopy is the interaction of light with matter. So we can interact visible light with matter, ultraviolet, infrared, and we get information from that molecular orbital theory. Another way we can apply quantum mechanics to bonds is by using valence bond theory. Valence bond theory is a simplified version of this. The full quantum mechanical treatment is, the disadvantage here is this is difficult. And so valence bond theory just aims to simplify things by making some assumptions which aren't entirely correct. And so this would be called the quantum mechanical light version. But with the light version, you got to sacrifice something, and the things you sacrifice are things in terms of accuracy. That is, typically, we don't get things like spectral data. Is not obtained using valence bond theory. Sometimes the structures and the energies, the energies are going to be wrong. The energies will be off. I shouldn't cancel this completely out because we do get some information about the energies. And sometimes it's just wrong. For example, it fails. And it fails for molecules that are simple, like O2. O2 is probably the biggest, most well-known failure of valence bond theory, etc. But the big advantage is it's easy. This is difficult, this is easy. And so let's take a look at both molecular orbital theory and valence bond theory and just get a little comparison between the two. MO theory is molecular orbital theory, so we'll just call it MO theory for short. MO theory, when we think about a bond, what is a bond and how's a bond made? In MO theory, we have things called molecular orbitals. And so you've learned atomic orbitals. The atomic orbitals would be like an sp, d, etc. Well, you'd learn a new set of orbitals, and these new set of orbitals would apply to molecules. And this new set of orbitals would be things like the sigma 1s orbital. The sigma 1s orbital spans the entire molecule. So if we're looking at a molecule, A bonded to A, let's say, this would be a diatomic molecule. The molecular orbital would be something like this, where here's the nucleus of atom A on the left, here's the nucleus of atom A on the right, and this would be just one orbital. This one orbital has a max capacity of 2 electrons, just like an atomic orbital, but it's big, it's a molecular orbital. And we have a bunch of these, etc. Whereas in valence bond theory, it's a little different. When we look at VV theory, we are dealing with atomic orbitals. Our familiar atomic orbitals. And so an example of this would be if we're looking at H2. H2, you have a hydrogen 1s orbital here, and another hydrogen 1s orbital here. And so we can form the molecule H2. And so we retain our atomic orbitals in valence bond theory, but in molecular orbital theory we don't, because H2 wouldn't have 1s orbital here and a 1s orbital here. Instead, an H2 molecule would have something called a sigma 1s molecular orbital instead. How we describe a bond is slightly different too. In MO theory, a bond is described as having electron density, net electron density in the internuclear region. The internuclear region is going to be dictated by having a sigma type bond. And so that electron density here, net electron density here, will hold the two atoms together. And so we have nucleus here, nucleus here. The two nuclei are going to be attracted to negative charge density regions. Negative charge density regions would be this green region here. Well, that sounds like the same thing as valence bond theory. In valence bond theory, the atoms are going to be held by having net negative charge density in the internuclear region. Internuclear would just be the region between the two nuclei here. And so if we have these two atomic orbitals like this, we'll see that the probability clouds are going to look like this. And where the probability clouds overlap, we're going to get a higher density of dots. And so the two nuclei are going to be attracted to the negatively charged region, which is green in this case, and hold the two nuclei together. And so when we talk about bond, in valence bond, it's like this. A bond is equal to overlap of atomic orbitals. When we look at molecular orbital theory, a bond is equal to having net electron density in what I'm going to call a bonding molecular orbital. Net electron density in bonding MOs. Let me continue with the MOs, because when we generate MOs, this is a continuation for MO theory here. When we generate MOs, probably the easiest way to generate the MOs is by doing something called LCAO. LCAO stands for linear combination atomic orbitals. And so, as I said before, when we're comparing hydrogen using MO theory, there's no atomic orbitals here, it's just molecular orbitals. This is the full quantum mechanical treatment. This is still quantum mechanical because orbitals, atomic orbitals come from quantum mechanics. But it's not full quantum mechanical because what we do with atomic orbitals, here we're just overlapping them, not doing this. We should be doing this. This LCAO, linear combination of atomic orbitals, is how the orbitals mix. And so if I have an atom of hydrogen over here, I have a 1s orbital. And then over here, I have another atom of hydrogen. This is a 1s orbital here. And when I mix these together, there are two ways to mix these wave functions. So if I recall, the wave function for hydrogen looks like this, right? This is a positive amplitude here. And so this is the 1s, the psi 1s orbital here. If this is one hydrogen and I take another hydrogen here, and this is going to be the psi 1s orbital here, then when I mix these two together, positive amplitude and positive amplitude, I'm going to get something like this, right? This is what we call the sigma 1s orbital here, like that. And the sigma 1s, when I look at a 90% probability boundary, and we traditionally show these dashed lines to show that the orbital is going to look like this. It's going to be a cigar-shaped orbital. It's big because it spans the entire molecule, but it's not so big in that it can only hold 2 electrons max. And so this orbital is just like an atomic orbital. It's going to follow the same rules, and that is, 2 electrons max with opposite spin, one spin up, one spin down. That's one way of adding these, but if on the other hand, we added it like this, let's say I took this wave function and left it positive amplitude, but flipped this one upside down, made it negative amplitude. And so if I try to mix these two, are they going to mix a positive and, no, this is going to create a different type of orbital. And this different type of orbital here is what we call a anti-bonding orbital. The reason it's called an anti-bonding orbital is because where the electron density is located. And so here's one lobe and here's another lobe. This is one orbital here. And so this orbital down here is called a sigma 1s. This orbital up here is called a sigma 1s star. Sigma 1s star is higher in energy than a sigma 1s. And so a 1s orbital, this has capacity for 2 electrons, this has capacity for 2 electrons. So there's something called conservation of orbitals in this case. Because when I do an LCAO of 2 atomic orbitals, I generate 2 molecular orbitals. The 2 molecular orbitals I generate depend on how we mix the wave functions in terms of the amplitude there. And so here we have a constructed one, which we call a bonding MO. It's a bonding MO because when I look at the electron density of the cloud, this has maximum capacity of 2 electrons, and those 2 electrons are going to occupy this space. And what holds the two hydrogen together are the attractions of the positive nuclei with the negative charge density in this region. On the other hand, this orbital up here is called an anti-bonding MO. Because if I put electrons here, and this has a maximum capacity of 2 electrons as well. If I put those 2 electrons up here, then if you look at this, most of the negative charge density are outside of the internuclear axis here. And that is, if I have the negative charge density behind this one and behind this one, then the 2 nuclei are going to see each other. If the 2 nuclei see each other, then they're going to repel each other due to their positive charge. Like charges repel. And so this, having electrons here in this molecular orbital does not help bonding. In fact, it hurts bonding. And so we can come up with an equation over here. In order to get net electron density in the bonding MOs, I have to make sure that I have more electrons in the bonding MOs than the anti-bonding MOs, and then I'll have net negative charge between the 2 nuclei, holding the 2 nuclei together. If I have equal amounts, let's say I have 2 bonding electrons and 2 anti-bonding, then the anti-bonding will cancel out the bonding and we get no bond interaction. And so down here we can write an equation. The equation is going to be like this. The number of bonding electrons minus the number of anti-bonding electrons divided by 2 is equal to the bond order. And so normally when we think about a single bond has 2 electrons worth of density in the bond. And so bond order 2 would be a double bond. A bond order 3 would be a triple bond. And so we'd have net, 2 electrons. Let's say I had 2 electrons in the sigma 1s here, which is a bonding MO, and no electrons here, then that would be equivalent to a single bond. And so the way the 2 theories describe bonds are slightly different and at the same time similar, because both of them are going to rely on having electron density in the internuclear region. When we have electron density in the internuclear region, it can be directly along the internuclear axis, and this type of bond here, which is the overlap of a 1s bond with 1s orbital with a 1s orbital here, this is actually called a sigma bond. It's a sigma bond. And so this would be a 1s referring to this orbital, and a 1s referring to this orbital, a 1s sigma bond here. Now 1s sigma bond is not the same thing as a sigma 1s MO. In fact, these shouldn't be confused, even though they use the same nomenclature here. A sigma bond is not the same thing as a sigma bonding MO. In certain respects they're similar, but in other respects they're totally different. In fact, they are totally different. The only thing is they kind of look the same. I mean, if you look at the green clouds, electron density, they sort of look the same, right? But they're totally different. This sigma bond, when we say sigma bond, that's referring to valence bond theory. And when we're referring to valence bond theory, we're looking at the overlap of atomic orbitals. When we say sigma MO or sigma bonding MO, then we're looking at a single orbital. Just because we have a sigma bonding MO doesn't mean there's a bond there. Because if we have a sigma bonding MO with 2 electrons and we have a sigma anti-bonding MO with 2 electrons, there's no bond. The bond densities cancel each other out. But not bond, but electron densities cancel each other out. And so the nomenclature's mixed up sometimes, but you shouldn't get mixed up because these are referring to 2 totally different things. So let's continue our comparison. In valence bond theory, we could have another type of bond called a pi bond. A pi bond looks a little bit different because of the way the orbitals overlap. And so if we look at two p orbitals, like a px orbital on atom A and a px orbital on atom B here. And so we can form an AB bond here by overlapping a px orbital here with a px orbital here, and we can overlap them head-on like this. This would be called a p-p sigma bond. And a sigma bond means that there's overlap within the internuclear axis. The internuclear axis, we could draw a line connecting the two nuclei. So there's the nucleus of atom A here, the nucleus of atom B here. And when we look at the overlap region here, we see that there's overlap within the internuclear axis. It's a sigma bond. We can also have a pi bond. A pi bond has overlap outside the internuclear axis. So if we're looking at a py orbital here on atom A and a py orbital here on atom B, we have a bond occur because we have overlapping atomic orbitals. But where the overlap here is above the internuclear axis and below the internuclear axis. When we have overlap outside the internuclear axis here, we call this a pi bond. So this would be a p-p pi bond. Again, this is valence bond theory, because valence bond theory relies on the overlap of atomic orbitals. And atomic orbitals we already know. But if this is well, actually, is this more of a bonding or an anti-bonding interaction? Because if you look at that, the electron density's up here above the two nuclei and down here below. And so don't the two nuclei, I mean, the two nuclei are going to see each other and just repel each other. They're both positively charged. And so would this result in an anti-bonding type interaction? No. Well, this is going to result in a bonding interaction. The bonding interaction is like this. This electron, because we're going to have extra charge density here, is going to be attracted to the charge density above and the charge density below. And so net, the two nuclei are going to be drawn towards each other because of the negative charge up here and the negative charge down here. Okay. And so the two bonds, types of bonds we often see in valence bond theory is the pi bond and the sigma bond, depending on how the orbitals overlap one another. To confuse matters, in MO theory, we have pi MOs as well as sigma MOs, depending on how we do the LCAO. And for example, here, you know, when I do an LCAO of a px and a px orbital, so here's one px orbital on atom A. Let's go with another px orbital on atom A here, and so we're going to form the homonuclear diatomic A2 molecule. And so we do this. You know, this is the LCAO part here. It's kind of this plus or minus deal with the two wave functions. when they add constructively, that is, let's say this is positive and this is positive, right? Then we're going to form a bonding MO. The bonding MO is going to be the nucleus of atom A here, the nucleus of the other atom A here, and then there's going to be a net electron cloud here between the two nuclei. And so this is going to grow. And so we call this a sigma 2p, or sigma p. We'll just call it 2p. So we'll call this a 2px and 2px here. So this is a sigma 2p, in which there's electron cloud here, and a small lobe here, and a small lobe here. The 3 lobes. Okay, if they add the other way, how that is this subtraction here, then we're going to generate something that looks like this. Kind of a 4-leaf clover. It has 4 lobes. This is just one orbital. This one orbital holds a maximum of 2 electrons. Oops, this is wrong. Sorry, that's wrong. And it's going to look like this. 2 small lobes here, big lobe here, big lobe here. So if I look at there's no electron density within the internuclear region or even above or below it. The electron density is behind the 2 nuclei here. So the 2 nuclei are going to see each other directly, and we call this a sigma star 2p here. Sigma star 2p. And so in MO theory, we have to learn all the new molecular orbitals that are associated with molecules. Now let's show you one more set. And this one more set is going to come from an LCAO-PY. So I look at a 2PY here, and on atom A, and another 2PY on another atom A here. I do the LCAO. I'm going to generate a bonding MO and an anti-bonding MO. And so this is the conservation of orbitals I was talking about earlier. If we take 2 atomic orbitals, then we've got to form 2 molecular orbitals. One like this with positive, positive, negative, negative. The waves interact constructively. We end up with a lobe above and a lobe below. This is one orbital again with a max capacity of 2 electrons. This we call a pi 2p. And so the origin of the symbol pi in bonding theory comes from where the electron cloud is. Like if we look at a pi bond is going to have overlap above and below the internuclear axis here. If we look at a pi MO, well, pi MO is going to have electron density above and below. But, again, these two are not related. They're totally different. The only thing that is similar is where the electron cloud is. And since when you look at the electron cloud, is there really much difference in the electron cloud between these two? There really isn't that much difference. And so this is one of the reasons why we use valence bond theory. Really, if valence bond theory fails for a molecule as simple as O2, then should we really be using it? I mean, O2 is a very common molecule, and valence bond theory doesn't work. And so really, we should just use MO. But the problem with using MO is it's difficult, very difficult. And the advantage to using valence bond is it's easy, very easy. And so even though valence bond does give us the wrong answers sometimes the answer is not so different, because when you look at the electron cloud density here and compare it to the electron cloud density there, it's hard to tell the difference. They look pretty similar. However, when it comes to antibonding, the antibonding are going to look very different. The antibonding, there's no mixing here. So this is looking like a 4-leaf clover. There's going to be a node here. No electron density. So basically the two nuclei are going to see each other and the two atoms will separate. And so this is an anti-bonding MO, pi star 2p, anti-bonding. And so the reason we continue to use valence bond theory is, one, it's easy. Two, it gives us a reasonable picture of electron density sometimes. But three, if we want spectral information or we want energy, then we have to use MO. In order to do MO, you can't do it on pencil and paper like valence bond. Valence bond is simple enough, you could do it without any calculations. MO is quite complicated and you'd have to use a computer to figure out things. Except for simple, for simple molecules, like the simplest molecule would be a diatomic. And so MO is difficult. And so in Chem 1A, MO is restricted to simple diatomics. Valence bond is easy, and so valence bond we're going to spend the bulk of our time talking about because valence bond has wide application in Chem 1A. We can apply it to all molecules. All right, so let's go ahead and start applying our valence bond theory. So we're just going to focus on valence bond for right now, and then later on we'll come back to MO. So valence bond is good because we've already learned atomic orbitals like the S, the P, the D, and so all we have to do is look at overlapping those orbitals to make a bond in a molecule. And so let's take an example of valence bond theory here. If I look at fluorine, fluorine has a 1s2, 2s2, 2p5. Like that. And so I see one orbital capable of bonding. These orbitals are incapable of bonding because in order to bond, we have to overlap atomic orbitals. Well, these orbitals here do not want to overlap with other orbitals, otherwise there's going to be overcapacity of electrons. And so if on a fluorine, if I have a p orbital, let's say like this, and there's already 2 electrons here, and then I bring another orbital in here with an electron, there's too many electrons. Essentially that means we could get 3 electrons into this orbital here by sharing. If we get 3 electrons into a single orbital, that's a violation of the Pauli exclusion principle. So we wouldn't do that. And so it looks like fluorine's capable of forming one bond. In this. And so we have one 2p orbital that can overlap. It's got a radical or a dangling bond in there. It's just one electron. So let's take a look at that. So if I put a fluorine here, and I have let's go with a 2px. This 2px is one electron. And so another orbital can come in here and bond. For example, a hydrogen 1s orbital. Hydrogen 1s orbital comes in, bonds here, and form HF. That's one possibility. Like that. Now we have a bond in valence bond theory. Now what we have to do is we have to describe the bond. The bond is going to be described like this. When we have overlapping orbitals, we're going to have a higher probability of electron density being found in the overlapped region. This higher probability of electron density means that the two nuclei are going to be pulled towards this region of negative charge and hold the two atoms together. And so valence bond theory relies on the overlap of atomic orbitals, which results in a greater negative charge density between the two nuclei. And that negative charge holds the two nuclei, positive nuclei, together. Well, what kind of bond is this? Is that a sigma bond or a pi bond? In valence bond theory, we have two types of bonds: the sigma bond, which this is, and a pi bond, which this isn't. How can you tell the difference? Well, how you can tell the difference is you just look at the internuclear axis. Internuclear axis is here. Is the overlap within the internuclear axis? Yeah, so it's a sigma bond. And then we could get more descriptive. You know, this we could call a P-S sigma bond. If we wanted to get even more descriptive, we could call it 2P, 1S sigma bond. You know, a 2P, 1S. It's commutative, so it doesn't matter which one you write first. You could call it 1S, 2P, or 2P, 1S. It doesn't matter. Sigma bond. So when we look at the energy level diagram of fluorine, we see a hydrogen pops in here with its 1s electron, overlaps and shares that. This is going to complete fluorine's octet. In fact, oftentimes most books ignore the core electrons. Most books ignore core electrons. The core electrons don't participate in the bonding. They're just stuck in the core. What's going to participate in the bonding are the valence electrons, and the valence electrons are what we'll focus on here. And so I'm going to also ignore the core electrons and just look at the valence electrons. Looking at the valence, well, fluorine's just filled its octet by having hydrogen come in and share. Hydrogen has an electronegativity of 2.1. Fluorine has electronegativity of 4.0. And so 2.1 minus 4.0 gives us 1.9, which brings it into the polar covalent bond range. You know, it'd have to be a little bit bigger of an electronegativity difference to go into ionic. And so this is a polar covalent bond. All right, this is with a what we call valence bond theory in order to describe it. In valence bond theory, yeah, it looks like we have an energy level diagram here. If we have an energy level diagram, then we should be able to predict the electron transitions to higher energy. The next higher energy would be 3s followed by 3p, etc. But what happens is those energies are off, you know, because in reality, it's not AOs, atomic orbitals that we have, but in reality, it's MOs. An electron cloud density distribution is a little different. Sometimes it looks quite similar, though. But nonetheless, we'll draw this part just to show us, you know, what's happening with the orbitals here, so we can see. So if we're looking from hydrogen's perspective, hydrogen has a 1s orbital with 1 electron here. And then fluorine comes in and fills hydrogen, what we call a duet for hydrogen, because hydrogen only needs 1 more electron to fill its valence shell. And so fluorine comes in here with a p electron to complete hydrogen's valence shell. All right, let's take a look at F2. F2, we have 2 choices for how we bond it. You know, we could bond it like this. Here and here. What type of bond is this? If this were fluorine and this were fluorine, what kind of bond is that? That's a pi bond. Or we could bond it like this. You know, we'll just take a P here, and bond it. We'll get 1 electron here on this fluorine, 1 electron here on this fluorine. and we've reached capacity here. But if we bond it like this, you know, this is not a pi bond, this is a, what kind of bond? This is a sigma bond. What do you think is more stable? What do you think more stable means, what do you think is going to be a stronger bond? A pi bond or a sigma bond? A pi bond should be stronger? You have to look in terms of electron density. Both of these have the same capacity. And so we're going to have a limited number of dots. And the limited number of dots, let's say I have 1,000 dots. I draw 1,000 dots here versus here. And so maybe the clouds look somewhat similar, but in terms of dots, but the way the nuclei are going to be attracted are different. In the pi bonds, the nuclei are attracted to the negative charge regions here and up here because greater density in the overlap region here, here and here. And so the nuclei are going to be attracted up here and down here, and then net they're going to pull towards each other. Whereas here, the nuclei are attracted straight into the cloud here and straight into the cloud here. And so when you compare the interaction, which one do you think is a stronger bonding interaction, a sigma or a pi, and why? It turns out it's not a pi. The pi is weaker. It's weaker because the electron cloud is above and below, whereas here it's directly between. And so in general, sigma bonds are stronger than pi bonds. Sigma bonds are stronger than pi bonds. And so if we have a choice here, we should form the strongest bonding interaction. So it doesn't pi bond. Two fluorines don't pi bond with each other. Two fluorines will sigma bond with each other. They'll sigma bond with each other because having the electron's density or electron cloud within the internuclear axis is better. And so fluorine's going to look like this, where we have a fluorine here and a fluorine here, and we create a PP sigma bond. PP sigma. Again, this is not a sigma MO. You know, sigma MO kind of looks like that, but it's totally different in terms of thinking. And so what we do is we draw out the energy level diagrams, and now I'm going to ignore the core, so I'll just look at the valence here. And so one way of fluorine completing its octet is if another fluorine comes in. Another fluorine comes in and donates a 2p electron, so we call this fluorine 2p, comes in here and completes that octet. And so this would be one of the fluorines, maybe the left fluorine. And the other fluorine here, you know, 2s and then 2p. Oops, I have to flip the spin here, make it work. And this fluorine 2p comes in here and rejects it. So based on the perspective of both fluorines are happy because now both fluorines have an octet, and that octet was gained by sharing the electron. Here, sharing electrons. So we can apply this to other molecules as well.
What's what makes a fluorine gas so reactive then if it's too happy with, or the octet? So
What makes fluorine gas very reactive? That's a good question. What makes it so reactive is, you know, each fluorine, do you think fluorine really wants to give up any electron density? No, because it is the most electronegative. And in this case, you know, this is the best compromise. But if there's a victim that will readily give up an electron, that victim being like a metal, like sodium metal. If sodium metal was around, then what, you know, and you got to think of fluorine as being a predator. You know, the two fluorines can attack the sodium and take electrons, and in that way they don't have to share their electron density. And so the way we think about this in terms of like a physics type way is because Z effective on the outside of fluorine is very large. And so even though these are sharing and they've reached some sort of compromise, both of them are trying to pull the electron off the other. And it's not possible because they're both tied in terms of, and so you got two very powerful opponents, but they want they want the rope, or they want the electron, and so what they're going to do is they're going to find a more readily available victim, you know, in which it can fully take the electron. Okay. Well, let's go on here and take a look at some others for valence bond theory. These are going to be for molecular. Beryllium, you know, beryllium's very small. And so even though beryllium's a metal, its ionization energy is kind of high. And so beryllium difluoride does not form an ionic compound. And so beryllium isn't a great victim, but it's better than another fluorine. And so beryllium will get attacked by fluorines. In fact, beryllium forms the molecular compound beryllium difluoride. You do the Lewis structure, and we know that the FBEF angle is 180 degrees, correct? And so in valence bond theory, what we do is we overlap the atomic orbitals. That's what we do. And so in valence bond theory, one of the first things we look at are the atomic orbitals. So what are the atomic orbitals of beryllium in order to overlap them? Well, if we look at beryllium, well, I'll do the core here. Beryllium's got 2 electrons in the 1s, and its valence is the 2s here. And it's got 2 electrons in the 2s, and the 2p are empty, like this. Now, if I think about this, is this capable of forming a bond here? Let's say another orbital wishes to overlap with that 2s orbital. And so if I look at the beryllium's 2s orbital here, the 2s orbital already has 2 electrons. And so if some other orbital comes in here and tries to overlap, let's say a p orbital here, a p orbital comes in and tries to overlap with another electron, is that going to work? No, I mean, we're gonna get 3 electrons possibly in one orbital. 3 electrons in one orbital is too much. And so this is not capable of bonding. And so really beryllium should form maybe 0 bonds. But, you know, whatever theory we have, theory has to agree with experiment. And beryllium difluoride is a molecule that's been made and analyzed. And it consists of 1 beryllium and 2 fluorines, and it has a bond angle of 180 degrees. And so valence bond theory, any theory, has to explain experimental fact. If this is experimental fact here, then our theory just failed, right? Or did it? Well, we shouldn't give up yet on the theory because we could do something here. This is often done. Here, we've seen this happen. There's precedence for this happening. And so one of the things we can do is we can promote one of these 2s electrons into a higher energy 2p orbital here. And so if we do that, then we're going to get a single 2s electron here and a 2p electron here. Now this is capable of forming 2 bonds. And so what can happen is a fluorine can come in here and bond here, the 2p, and another fluorine, the 2p, can bond here. And so we can form these overlapping orbitals here. But, you know, these are 2 different orbitals, and when we look at the bond lengths are going to be very, actually not even very, they're going to be the same. These have exactly the same bond length here, but if we look at the theory here, the theory is one of these bonds is going to be a 2p2s bond, and the other is going to be a 2p2p bond. And so the two bonds look different, not the same. And so there's one more component to this. And not only that, what are the angles? The angles are going to be kind of funky. And so we'll talk about that in just a moment here. Actually, maybe we should talk about it now. And so if we have a fluorine here, a fluorine's got a 2s orbital here, and a 2p orbital, not fluorine, beryllium, and the 2p orbital here. The 2s orbital on beryllium has 1 electron. The 2p orbital on beryllium has 1 electron. And so maybe I'll shade these differently. Put the 2s vertical lines here. The 2p is horizontal lines here. Okay, so one fluorine comes in here. Just make it black. A fluorine comes in here and overlaps here. This will be a 2p on fluorine. And that would come in and overlap here. Okay, and then the other fluorine's going to come in, but where's the other fluorine going to come in? Well, it's got to overlap with the 2s orbital here, right? And we probably, if we bring the fluorine and bring it in here, then the fluorine would also overlap with the 2p orbital. Can we have 3 orbitals overlapping? No, because 3 orbitals overlapping are going to give us 3 electrons, which are going to exceed the capacity of each orbital. And so we've got to bring in the fluorine. Maybe we'll bring it here, like that, because the s orbital is spherical. So we can just bring it there. But if we bring it here like this, does that explain the FBEF angle? The FBEF angle is 180. And so really we should bring it here, but if we bring it here, then we got trouble. And so this does not work here. And so what's wrong? Well, maybe our measurements were wrong here. And it turns out the measurements weren't wrong. The measurements were correct. And so there's something else going on here. And the something else that's going on here is maybe our theory is wrong. No, our theory is wrong, but you know what they did to fix? They just fixed the theory by modifying the theory. And the way they modified the theory is by coming up with a new set of atomic orbitals. And so you've already learned the S, the P, the D. You'll also have to learn these. These are called the hybrid atomic orbitals. And so we have 2 sets of atomic orbitals. We have the unhybridized orbitals, the ones you already know, S, P, D. And then we have a new set of orbitals that are called the hybrids that you'll have to learn. And so let's talk about the hybrids. Let me just show you some of the hybrids right now. The first hybrid orbital is called the sp orbital. And there are 2 sp orbitals. Each sp orbital is going to look like this. So one sp orbital if I'm looking at atom A, is going to look like this. And the second sp orbital is going to look like this. It's going to look exactly the same, except it's just flipped to the other side. Actually, let's make this like this. Vertical. Make it look different. And so when I look at the 2 on the same atom, it looks like this. Here's the nucleus. Here's one of the sp orbitals, this. And here's another of the sp orbitals, like this. And so this takes care of our problem, because now I have two atomic orbitals oriented 180 degrees apart from each other. And so now it's simple. It's simple to see how beryllium is going to bond, because beryllium can bond an sp orbital here to a fluorine p orbital here. And so if I have one electron in this sp orbital, okay, this small lobe over here, sometimes this small lobe over here is not drawn, then what we form is an sps sigma bond, an sp p sigma bond. Okay, that's going to be on the right side, and then I have an sp orbital here on the left side oriented 180 degrees. These two sp orbitals are 180 degrees apart, which makes it very convenient, because I can have another electron. Now, you know, this is not having 3 electrons in one orbital, because even though it looks like a p orbital, it's not a p orbital. A p orbital has 2 lobes. Like that, and the max capacity of 2 electrons. This is 2 sp orbitals, which, you know, each sp orbital has a max capacity of 2 electrons. And I can bond the other fluorine here. Like this. This is a p. Actually, let's both. I'm going to point both of these up. Sorry, it doesn't matter spin up or spin down. Let's point them both up to emphasize that these are 2 separate orbitals here. Brilliant. So what does the energy level diagram look like for this? Okay, the energy level diagram is going to look like this. I'm going to have an sp orbital here, another sp. So I have my 2 sp orbitals. These are energetically degenerate. And each one of these will have 1 electron. And then fluorine comes in and bonds here and here.
Question, so is it just kind of like fused together, or like what happens?
All right, let's talk about where they come from, because in the energy level diagram, not only do I have these 2, but I have these p orbitals here. And so where do these hybrid orbitals come from? Okay, the way we're going to generate the hybrid orbitals is like this. Basically, they're a hybrid mix of regular atomic orbitals, unhybridized orbitals. Atomic orbitals, we'll just say AOs for short. And so if I have an s orbital like this, an s orbital is positive amplitude, and I do a mix of this here. Actually, there are 2 ways to mix it here. The plus and the plus are going to add, and the plus and the minus are going to detract. And so one way of mixing these 2 orbitals is like this, where you generate this. And so because of the positive amplitude here, this side adds constructively. There's a negative amplitude here on the p. This would be the p here, orbital here. The negative amplitude on here, this lobe's going to shrink way down. And this is 1 sp orbital. Oftentimes this little lobe here is just ignored completely, and it just looks like one lopsided lobe here on the right side. But we can also, you know, flip this, and so flip the s so its amplitude goes down. And then we generate this one, like this, where the negatives add constructively and the positives destructive. And so this would be the second sp orbital here. And so what it is, yeah, it's a fusing of the two atomic orbitals. If we kind of fuse an s orbital with a p orbital, this is what results in that fusing. We get two atomic orbitals yield two atomic orbitals. And so two unhybridized orbitals, I'm double counting this s because there are two ways of adding it. Two unhybridized orbitals, this is conservation of orbitals, yields two hybridized orbitals. Each orbital here is a 50-50 mix of s and p. That's why it's called sp. One part s, one part p. And this is what a one part s, one part p orbital would look like.
And you would have to include those probabilities.
Yeah. You mean both of these?
But yeah, for the version.
For which one? This one? Both probabilities, I mean, both amplitudes? Yeah, well, you would include, yeah, both of these you'd have to include because that's what we'll generate when we mix those. You know, there are two ways to mix them. It's kind of like the LCAO, but what we aren't doing is we're not generating antibonding here. And so this is the way we can visualize what's happening here. For BEF2, we do this. You know, for BEF2 doesn't want to form any bonds because it's filled. Two S's at least, two P's empty. So for something like BEF2, we have to first promote the electron. We promote the electron, that's going to cost energy. So, why would we promote it? Well, we promote the electron to maximize bonding. The more bonds we can form, the more stable the molecule should be. And so even though there's a cost associated with that, the return in energy is well worth the cost of promoting. This is the same thing that happens with the exceptions in electron configurations.
I guess my main question was, I pretty much just see one orbital there, when you combine the 2s and 2p, but you would have to include both.
Where do you see just one orbital? Because what we're doing is we're taking this 2s and the 2p, so that's two orbitals there, and then we're going to mix them, hybridize them. And so if I take the s and the p's and hybridize those, what I'll get is something 50-50 s and p. And so one part s, one part p, one part s, one part p. So I generate two orbitals from these. And it's because of the way we can mix it. You know, if we have the s as positive amplitude here, we'll mix it like this. If we flip it and make the s negative in amplitude, we'll do it like this because the negative and negative. See that? And so one of the sp orbitals is going, we'll just make it lopsided. So one was going to have a lobe on the right, the other is going to have a lobe on the left. Like that. Or however you want to do it, doesn't matter. And then we have our p orbitals here. These p orbitals are untouched, they aren't hybridized. And so for something like beryllium difluoride, this is the way we visualize it. An sp orbital here with one electron, and a fluorine 2p orbital. And so we have our sp p sigma bond. That's one. And then we have another sp orbital oriented 180 degrees from the fluorine p. And so we have a p-sp sigma bond. Then we have the p orbitals that are left over. And so we'll call one of these py. We got a py orbital here. Okay, a py orbital is going to have two lobes, max capacity of 2 electrons, but it's empty. There are no electrons there. It's the sp as in, and the fluorines contribute. So fluorine P is going to drop in here, and fluorine P is going to drop in here. So the Py is empty, and then we have a Pz. The Pz is also empty, no electrons there, and the Pz is going to stick straight out of the plane of the board, like this, and in. So this would be the Pz. Yeah. It's empty as well. And so this is what's happening with the bonding. And so what we've done is we've just taken our theory and just tweaked it so that it matches with experimental fact. That's it. Okay, there's another so how do we know what's going on? Actually, let's show you. How we know what's going on is based on the geometry of the molecule. And so the next type of hybrid orbital will be the sp2, that is 1 part s, 2 parts p. sp2, we have 3 sp2 orbitals. This will be an sp2 orbital, and these all look lopsided. And so it's going to have one big lobe here, one tiny lobe, which is often ignored. Another sp2 orbital here, lobe, and a third sp2 orbital here. And this is going to be a trigonal planar arrangement of orbitals. And so how we know what the hybridization is we memorize that sp2 is trigonal planar. And so if we see a trigonal planar group of electrons, it has to be a sp2 hybridization. Otherwise, we can't accommodate these at a 120-degree angle. The sp2 orbitals come from mixing your regular unhybridized atomic orbitals. And when we mix it, we'll take an S from the valence shell and 2 of the P's. And so these three orbitals are going to generate 3 hybridized atomic orbitals. Each one 1 part S, 2 parts P, 1 part S, 2 parts P, 1 part S, 2 parts P. And that leaves 1 P untouched. So that 1 P that's untouched is a PZ, which is going to be oriented, if we're looking at this trigonal planar arrangement, the unhybridized P is going to be sticking, one lobe of it is going to be sticking right out, and the other lobe is going to be sticking underneath the plane. So this would be what we call the top view. This is looking straight down the z-axis here. We can rotate this 90 degrees to get something of a side view of this. And so the side view of this might look something like this, where here's an sp2, and so we'll form a trigonal planar arrangement of sp2 hybrid orbitals here, this. And so here's our 3 sp2 orbitals in a trigonal planar arrangement, but now we can see the pz orbital in profile. The pz orbital is just going to have 2 lobes like this, or an arrangement. We call this a side view. And so how do these sp2 orbitals form? Well, it's mixing s and 2 p's quantum mechanically using the properties of waves we talked about briefly earlier. It's sp2. So let's see, did I miss something? How did I get so far ahead? This class. Well, let's talk about how we determine hybridization. Hybridization is determined from the Lewis structure, not from the atom. The reason it's determined from Lewis structures like carbon. You know, carbon, the atom can form linear, can form trigonal planar, it can form tetrahedral structures. If we have linear structures, then the bond angle is 180. If we have trigonal planar structures, the bond angle is 120, and if we have tetrahedral, the bond angle is 109. And so it's not because it's carbon that it's going to be hybridized in a particular way. Hybridization is going to be determined from Lewis structure and groups of electrons. And so we just base it on the number of groups of electrons. If there are two groups of electrons, then we have a linear arrangement, right, of groups. In order to get a linear arrangement of orbitals, then the hybridization is to be sp, because all the other hybridizations are going to give you a different angle between the groups. So linear will be 180 degrees. If we have 3, then it's going to look like this, trigonal planar. And so we put groups of electrons here, one group of electrons here, one group here, one group here. And therefore we can get a trigonal planar arrangement of groups. Whereas we wouldn't be able to get a trigonal planar arrangement of groups, let's say, in using regular atomic orbitals unhybridized. And so this is going to be sp2. If we have 4 groups, then it's tetrahedral. And it's going to be sp3. 5, it'll be square, not square, trigonal bipyramidal. And this is sp3d. We've got to hybridize a d orbital along with the s and the p's. And if it's 6, it's octahedral. And the hybridization is sp3d2. And so we look at the groups. And so let's look at something like BF3. There's an example here. BF3, boron trifluoride. The first thing we do is draw the Lewis structure. We draw the Lewis structure like this. We see, okay, that boron's going to have less than an octet. Why does boron have less than an octet? Why don't we just form a double bond here? Formal charge would be bad. If we form a double bond here, fluorine would get a positive formal charge, boron would get a negative formal charge. So essentially, if we double bond here, fluorine's giving up an electron to boron. It doesn't want to do that. Not to boron. All right, then we look, you know, this is valence bond theory. And so valence bond theory, we've got to look at the orbitals. As we're looking at the orbitals, boron is 2s2, 2p1. 2s2, 2p1. Is that it? Yeah. 2s2, 2p1. How many bonds is boron capable of forming? Yeah. Like this, boron's only capable of forming 1 bond, right? 1 bond. That's not looking so good. And so what can we do here? We're going to promote an electron. And so you promote an electron. Why promote? Because it seems to, so here's our 2s, here's our 2p. So we promote an electron. Now we're capable of forming more than 1 bond. Now we're capable of forming how many bonds? We promote to maximize bonding, right? Maximize bonding. And so if a fluorine came in here, okay, fluorine can come in here and bond. So now we can form up to how many bonds? 3 bonds. And so we can form 3 regular bonds. I'll just say normal bond. What is a normal bond? A normal bond is where you have one orbital on boron overlapping with one orbital on fluorine. The boron provides 1 electron, the fluorine provides 1 electron. So each atom provides 1 electron. Okay. Or we can form 3 normal. Normal is not the right word for this. It's called 3 bonds. Plus 1, what we call a coordinate covalent or dative bond. A coordinate covalent or dative bond is a special type of bond. In this bond, what we'll see is this. Okay, let's go, the 3 normal bonds are going to be as is, you know. We got these 3 orbitals like this, singly occupied. So fluorine comes in here, here, and here. But what can happen is this. Another atom can come in here. But if because there's an empty orbital, do you see this empty orbital? The problem is if this other atom comes in here, which we'll call B, atom B has to supply both electrons for the bond. And so this is what's called a coordinate covalent bond. A coordinate covalent bond, or both bonding electrons, come from a single atom. In this case, atom B. I chose B because, do you know what the definition of a Lewis base is? Do you guys know the definition of a Lewis base? Electron pair donor. And so what has to happen is a Lewis base comes in and donates an electron pair to an empty orbital. And then we form a bond. And so this means that boron trifluoride is Lewis acid. It's got this empty p orbital here. This empty p orbital can be attacked by a Lewis base. And do that. And so that's Lewis bases form coordinate covalent or dative bonds. And form coordination complexes. Well, we're going to ignore that for right now. We're just going to look at this. Okay, we determined the hybridization from the geometry. And so let's go back here and not talk about this. When we look at the geometry of BF3, BF3 has a trigonal planar group geometry. Since it has a trigonal planar group geometry, what we need 3 orbitals at a 120 degree orientation. To get 3 orbitals at 120 degree orientation requires sp2 hybridization. And so what we'll do is we'll hybridize that sp2. And so we have 1 part s, 2 parts p, 1 part s, 2 parts p, 1 part s, 2 parts p, 3 orbitals like that, and then 1 unhybridized p. And boron's going to have 3 valence electrons like this. So this will be boron. And then the fluorines can come in here. Fluorine comes in here. Fluorine comes in here. Fluorine comes in here. Now, why does it hybridize? what would boron form these hybrid orbitals? The reason it hybridizes is to minimize repulsions. Because if we didn't hybridize, we would get something like this. If we didn't hybridize this, we had a boron here. Let's call this a py orbital here. So we have a py, and the fluorine would come in here and bond here. And let's call this a px. The px I'm going to code it a little differently. So the py, let's write this, and the px, let's write like this. So if a fluorine came and bonded here, and a fluorine came and bonded here, what would the FBF bond angle be? If you look at the FBF, well, it depends. You know, if I have a PY here, and I have a PX here, then a PY is on the y-axis, a PX is on the x-axis, and the FBF angle should be 90 degrees. Well, 90-degree repulsions are kind of significant, and so what it tries to do is it tries to spread out. The spread out, you aren't going to have p orbitals spread out. What you're going to have to do is you're going to have to mix it with some S character. And when it mixes, then you're going to get this spreading out. And so we go from a 90-degree angle to a 120-degree angle. And that's going to greatly reduce the repulsion here. And so hybridization is there. It's possible if we mix, you know, some S character into the P to minimize. Now we get an FBF angle of 120 degrees for all of them. So the fluorines come in here. Okay, each of these are sp2, 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 and we form an sp2p sigma bond. sp2p sigma bond. This pz orbital is open and empty, and so boron can easily be attacked. And in fact, it wants to be attacked because it has less than an octet. And so boron trifluoride is a very highly reactive Lewis acid because of that. All right, let's take a look at methane next. If we look at methane, we want to apply valence bond theory to this. So we got the Lewis structure, this, and then we draw out the structure. And methane should form a tetrahedral arrangement like that. Okay, if we didn't do anything and we look at the valence electrons of carbon, we have 2s2, 2p2. And so normally, without doing anything, carbon is capable of forming how many bonds? Well, 2 normal bonds, and possibly 2 normal bonds plus a coordinate covalent bond. So 3 bonds max. Well, 3 bonds max, well, that's going to be good, but 4 bonds is better. That's going to be even more stable. And so we do the same thing for carbon. We promote an electron. If we promote an electron, then we can form 4 bonds. And so the first thing is we want to be able to form 4 bonds. So that means splitting up the s electrons to get 4 single electrons like that. Now we're capable of forming 4 bonds. And then we look at the Lewis structure and determine the hybridization. We look at the Lewis structure and we see that we have 4 single bond groups. 4 groups means we need 4 orbitals. 4 orbitals in a 109.5 degree orientation. And those are going to be hybrid orbitals. So if we take one s and a p and a p and a p, that gives us 4 orbitals. And so we hybridize all 4 of these to generate 4 new orbitals. All of them are going to be exactly the same, and they're all sp3. 1, 2, 3, 4. And when I look at these sp3 orbitals, they're going to be in a tetrahedral geometry like that, and they're all at 109.5 degrees. So that'll give us the correct structure for methane. So we're going to continue this next time, actually tomorrow. Let's see then. We'll stop here.